So in this video we go over section 1.6 equations in inequalities involving absolute values. So we will begin with solving equations first, but before solving the equation we need to review what absolute value is so we can have a good understanding of what we do every time we solve an absolute value equation. So the absolute value of a number denoted whatever number with bars, vertical bars on the sides. It means the distance from 0 to a on a number. For example, so let me put it this way. So the distance from the number 0 to 3 on the real number line is 3 units. So the absolute value of 3 is going to be 3. Okay. In the same way, the distance from 0 to -3 on a real number is also 3 units. So the absolute value of -3 will be 3. Okay, graphically, so we're going to start at 0. Absolute value of -3, it's going to be here, and absolute value +3. Okay, so what we're really looking at is how many steps do we need to do to make in order to get from 0 to 3 and from 0 to -3. And in this case, how many steps or how many units? This is 3 units. 3 units. You can think of this like walking. So if you are standing at a point, then you do 3 steps forward, all right? And then you do 3 steps backwards. But when the moment you walk 3 steps backwards, that doesn't mean you are doing a negative distance. It's still a positive distance, but it's only 3 units in the opposite direction, backwards or to the left, as opposed to forwards or to the right. Now, how do we interpret equations that deal with absolute value? So for example, let's consider this equation, the equation absolute value of x equals to 3. This equation in essence is asking what are the real numbers that are 3 units away from 0 on the number line. Alright, so in this case, I'm going to start my center at the number 0. And we are going to answer this question that it just highlighted. What are the numbers that are 3 units away from 0? So in one direction, this is 3 units away, and in the other direction, this is 3 units the other way around. 3 units, 3 units. Okay. So the solution to the equation absolute value of x equals to 3, it will be 2 solutions, x equals -3 and x equals to +3. This definition, this theorem states that in a more formal fashion. So if a is a positive real number and u is an algebraic expression, then solving an equation of this form, absolute value of u equals a, is equivalent to solve u equals a or u equals -a. So in this case, the x plays the role of u, so we break this up into 2 different equations. Let's look at more solid examples to have a better overview of what it means to solve an absolute value equation. So these are the steps that we are going to follow to solve absolute value equations. So we are going to isolate the expression containing the absolute value. A very common mistake is to delete, or rather to erase, the absolute value of ours, which we do not do until we break that up into 2 equations. Then we do the breakup. Notice the breakup here doesn't involve absolute values anymore, and then we solve each individual of these equations. So let's do one example. The first example, we have absolute value of x minus 2 equals to 3. Okay, so in this case, the first step is already done for us, right? So we don't need to add or subtract a number because the absolute value expression it's already by itself. So we are going to write x minus 2 equals to negative 3 and x minus 2 equals to positive 3. So in this case, the number 3 plays the role of a right there. So we need to write two equations, one with the negative sign, the other one with the positive sign. So all we do now is solve each individual equation. Okay, so add 2 to both sides. Add 2 to both sides. So we are going to get x equals negative 3 plus 2, that's negative 1. That's the first solution. And the second solution will be x equals 3 plus 2, which is 5. Alright? So yes, we broke this up into two equations, and we solved this into two, and we got two solutions. But what does it mean graphically, and how do we connect this with the definition? Alright, so let's write this in terms of the true meaning. The true meaning of this, of solving an equation like this, is, so this equation, which I'm pointing it out, this equation asks which numbers are 3 units away from 2. All right, which units are 3 units away from 2? Okay, that is the question. So let me write down a number line first. I think it would be best to do that. I'm going to locate the number 0, 1, 2, 3, 4, 5. That's enough. Negative 1, negative 2, negative 3, negative 4, negative 5. So we're going to have all that number line there. Okay, so what are the numbers that are 3 units away from the number 2? So in this case, our center value will be the number 2, which I will draw with purple here. Okay, so 3 units away from that number. In the positive direction, I'm going to add 3. I'm going to move 3 steps rather. 1, 2, 3. 3 units. And on the other direction, I'm going to move 1, 2, 3. Also 3 units. So what are those numbers? Aren't they negative 1 and 5? Just the same numbers we got by solving the equations. So that is what it means to solve an absolute value equation. Alright? The numbers that are 3 units away from the center, from the center 2 in this case. Alright? So, do we have to do all this every time we solve an equation? No, not really. All you need to do is just follow the procedure, break it up into 2 equations with no absolute value bars, alright? And then solve each individually, and those are the answers. The reason for which I did this this image right here is just to give you a better overview of what it means to solve an absolute value equation. So let's do another example. So in this case, as opposed to the previous one example, we don't have the absolute value by itself. So the first thing we do is subtract 3 to both sides of the equation. Okay, and we get absolute value of 3x minus 2 equals 7. Alright, and then this is the part where we break it up into the -7 and the +7. One negative, one positive. What do we do? Add 2 to both sides to get 3x equals 2 minus 7, that's a -5, and divide both sides by 3 in this case to get x equals -5/3. That's one solution, right? And the other solution, okay, subtract 2 to both sides. By the way, I made a mistake here. This should have been, this must have been a negative, -2. So let's add +2. Alright, so 3x equals 9 and divide both sides by 3 to get x equals to 3. So two solutions in this case. Alright. Let's look at example C. This is a very interesting case, so we don't have this absolute value term by itself. So -7 on both sides, subtract 7 to both sides. 2x plus 5 equals 3 minus 7 equals a -4. So in this case, I'm going to stop at this equation and call it a no solution. Let's explain. Alright, so let's go back to the previous page. So let's go back to the definition of absolute value. So that's why I didn't want to define everything and rather be more specific to the example that I was just doing with the definition. So in this case, distances are positive. Like we mentioned earlier, it doesn't matter if you move forward or backward, you are counting the number of steps that you move. So you don't when you walk backwards, you don't say, oh, I'm walking -3 steps or I'm walking -10 steps. No, you're going backwards 10 steps, which is a positive number of steps because you are able to see those steps. So in this case, the reason why this is no solution is because absolute value are distances. And these are meant to be positive. So there's no way we get a negative distance, so that's why we call it a no solution for this one case. Okay. Now let's move on to the next topic, absolute value inequalities. Now we're going to look at these two cases, absolute values inequalities involving the less than or equal, and then in the last topic we'll look at inequalities the other way around. Okay, so just the same way we consider the first equation, we're going to look at an inequality, x, absolute value of x less than 3. This inequality is asking which real numbers are less than 3 or less from 0, are less than 3, are 3 or less units away from 0 on the number line. Alright, so in this case, let's start at 0. Alright, I'm going to start at 0 and I'm going to move to the right. Is the number 1 a number less than 3? That's the question. That is correct. The answer is yes. 1 is less than 3. I'm going to move forward to the number 2. Is the number 2 less than 3? That is correct. I'm going to shade that. I'm going to include that number. What about the number 3 itself? Well, maybe not quite 3. How about 2.5? 2.5 is less than 3, 2.7, and then 2.9. In this case, I'm going to stop here using bracket. So all these numbers, I mean not bracket, parentheses, because of the inequality sign less than, not less than or equal. Now let me go the other way around. What about the number -1? Is that 3 units or less away from 0? Which is correct. That is correct. Same with the number -2. It's also 3 units away or less than 0. And same case here, we can approach -3, but we do not include the number -3. All right. So in this case, all these numbers, this interval is all numbers that are less, or that are 3 units or less from 0. And in this case, we write it as -3 to +3, or using the inequality notation this way. All right. In this case, we have one of those compound inequalities like the ones we did in the previous video. And in a more formal way with symbols, so if we have an inequality of the form absolute value b less than a, it is exactly the same as solving this 3-side inequality without the equal bar of equality, as opposed to absolute value of u less than or equal a, we just include the equal sign bars. All right. So let's look at some examples and remarks. So in this case, inequalities that have this form have no solution. Why is that? Because, well, you have a distance here, a distance that is meant to be positive. Can we have something less than 0, a distance less than 0? No, that'll be a negative distance, so that's why that is no solution. However, as well, inequalities of the form u less than, absolute value of u less than or equal 0, they are equivalent of solving only the equation, because if we break this up into cases, we are going to have the following. We're going to have this is the same as looking at u less than 0, absolute value, and absolute value equals 0. So this one we already discussed over here, no solution, so we only look at this guy right there. Okay, so let's solve the following inequalities. So in this case, u equals 3x minus 9. 3x minus 9 will play the role of u, and the number 6 will play the role of a. So this is what we do. We are going to have an inequality of this form, of the second form, in which u will be in the middle, in this case the quantity 3x minus 9, and it will go less than or equal +6 and greater than or equal -6. Okay, so that's one. Now we need to solve this inequality for x. That is, our goal is to keep x in the very center. So add 9 to both sides. So 9 minus 6, that's a 3, less than or equal 3x, less than or equal 6 plus 9, that's a 15. Now in order to get the x by itself in the middle, divide both sides by, or rather the 3 sides, not both sides, the 3 sides by 3, get 3 divided by 3, that's a 1, and that's also just x, and 15 divided by 3, that's a 5. So that's the solution that we need to write using interval notation. It goes from 1 to 5, but we are going to put brackets in between because of the inequality symbols involve the equal inclusive brackets. Okay, and if we want to illustrate this using a number line, because most likely in the homework that'll be the case. Okay, this is where our 0 is, and all we do is goes from 1 to 5. It doesn't have to be perfectly scaled as long as it is correctly displayed, right? So this goes from 1 to 5. 1 isn't greater than 0, of course. No need to be perfect with the graph, but need to be consistent. Okay, let's look at another example. So we need to isolate the inequality, the absolute value term first. So to do that, we add 12 to both sides. So we get absolute value of 5x plus 8 less than only 12 plus 4, which is 16. And then from here, going back to the forms, all right, going back to the forms that we had from before. In this case, 5x plus 8 will play the role of u, and the number 16 will play the role of the letter A in our form. So let's break this into 5x plus 8 greater than negative 16, the negative number, and the positive number 16. Right, so we're good to go here and solve inequality. Subtract 8 on the 3 sides of the inequality to get 5x less than 16 minus 8, which is 8, and negative 16 minus 8, that is going to be negative 24. The last thing we need to do is divide both the 3 sides by 5. Okay, so final answer, x less than 8/5 but greater than negative 24/5. Again, we need to write this using interval notation. That's not really hard. All we do is write the numbers 24/5 and 8/5. But in this case, for the endpoint symbols, the grouping symbols are going to be parentheses as opposed to the previous example in which we had brackets. And the reason why is because we only have less than, not less than or equal, so we don't include this. So in this case, to draw a graphic representation of this, so your 0 is in the middle. That's always a good reference. Well, the negative 24/5, you don't even need to care how much is that in decimal, just as long as it's below 0, that is enough. And 8/5 as long as it is above 0. So we look for all these numbers right here. We shade them, this interval, negative 24/5, 8/5. Let's do another example. In this case, we don't have the absolute value term by itself on the left hand side of the inequality, so what we're going to do here is to subtract 12 from both sides. Okay, so in this case, we're going to have the absolute value of 5x plus 8 less than negative 8, and in this case, this is one of those special cases in which no solution. And the reason for which this is no solution is because, again, absolute values represent distances, so this is meant to be positive. Can we have something positive less than anything negative? That's impossible. Okay, so no solution. That's why. Again, because no positive quantity could be less than negative number. For example, let me do some examples. Okay, less than negative 8. the number positive 1. Is the number positive 1 less than negative 8? That's false. Is the number 17 less than negative 8? That's also false, right? It's not possible. Now we're going to review absolute value inequalities involving the other way of the symbol. So we consider the inequality absolute value of x, and let me make a slight change here to the notes. I'm gonna make it greater than or equal to make it easier. I should have done that on the previous case to understand it better. All right, so this inequality is asking essentially, okay, let's highlight the inequality, which real numbers are more than 3 units away from 0 on the number line. And let me fix something as well. Are 3 units or more. Okay, 3 units or more away from 0 on the number line. Alright, so in this case, this is what we do. Again, 0 is the beginning. 0 is where everything starts. So the number 0. Okay, I'm going to move 1 unit to the right. Is the number 1 3 units or more away from 0? So no, it's not the case. What about the number 2? Is that 3 units away or more? That's not possible either. Let me move over here. The next step. Is the number 3 units away from 0 or more? Yes, that's the first number. What about the number 4? Is that 3 units or more away from 0? That is correct. And then 5 as well, and 6. All these numbers are going to be 3 units away from 0. What about the other direction? Let me move into the left. Is the number negative 1 3 units away or more from 0? Not the case. What about the number negative 2? Is not 3 units away from 0 either. What about the number negative 3? That starts being the case. And also the number negative 4 is 3 units or more away from 0. The number 5 as well, and the number 6 as well, etc. And so on and so forth. So in this case, it's going to be this interval and goes all the way forever. All right, so what is this going to be the solution? So in this case, we're going to have x to be greater than 3 and x less than negative 3. Or we use the symbol, the grouping symbol from sets, the OR symbol. Okay, and in a more formal fashion, we have it this way, in which we have some u, which represent any algebraic expression to be greater than a number. It is equivalent to solve two baby inequalities. Okay, so let's look at one example. Let's look at a couple of examples rather. So the first case, and I might leave this paper here as well for reference. All right, we are going to have absolute value of 2x minus 5 greater than 3. If we observe the two cases, which is it's going to be the first one. So 2x minus 5 plays the role of u, and the number 3 will represent the role of a. Alright, so in this case, when we have an inequality like this, what are we going to get? We are going to write 2x minus 5 greater than 3, or 2x minus 5 less than 3. So we are going to solve two different inequalities. All right, two different inequalities. So add 5 to both sides. Oh, I forget the negative sign here. This negative sign that is right here should be right there as well. So I'm going to add 5 to both sides to get 2x less than 5 minus 3, which is 2, and divide both sides by 2 to get x less than 1, or add 5 to both sides, we get 2x greater than 3 plus 5, which is 8, and divide both sides by 2 greater than or equal, greater than 4 only, not greater than or equal. Now we need to represent this using a graph and using interval notation. But for this case, first of all, what we are going to do is represent this in a number line, because from this visual, from the visual front of the graph will be better to look at the interval notation for this. Okay, so we are going to locate the number 1 and we're going to locate the number 4. So all the numbers less than 1, that is the numbers, all the numbers below, all right, below 1, and x greater than 4, all the numbers to the right of 4. So in this case, represent this using interval notation. This will be negative infinity to 1. The union symbol, which represents the or, so the fancy math symbol to the English word or, and 4 to positive infinity. Okay, and that is our final answer. Let's look at another example. 4x, absolute value of 4x minus 8 greater than or equal negative 8. Okay, so first of all, we need to isolate the absolute value term. All right, and we do that by doing the following. We do add a to both sides. So we get 4x plus 3 greater than or equal egg minus 3, which is 5. Now, going back to these forms right here from the previous page, let's make some overlapping here so we can observe what is going to be what. So in this case, it is the expression 4x plus 3, which plays the role of u, and the number 5, which plays the role of a. Okay, so now that we know which one is which, we break this up into 4x plus 3, the number 5, or 4x plus 3, the number 5. In this case, we just go with the symbol greater than or equal 3, but in this case, less than or equal negative. Okay, negative. One case is negative, the other one is positive. Okay, let's recall that over here. This way is negative, the other case is positive. So let's see. Let's solve each individual inequality by subtracting 3 to both sides of each. That's going to give us 4x less than or equal negative 5 minus 3, that's negative 8. In this case, notice even though we have negative numbers being involved in the process, I did not reverse the inequality sign. And that's because that's not the case. The only case in which we reverse the inequality signs is when we multiply or divide both sides of an inequality by a negative number. In this case, we are subtracting, not multiplying or dividing. So that's why we still keep the same sense of the inequality. And finally, we divide both sides by 4. X less than or equal negative 8 over 4, that's negative 2. So that's the first inequality. Then or, so 4x greater than 5 minus 3, that's a 2. And divide both sides by 4 to get x greater than 2/4, which is 1/2. So before writing that using interval notation, let's locate these two numbers in the number line. The 0 in the middle always works. The number negative 2 is right here, rather negative 2. And the number 1/2, it's somewhere here. It doesn't have to be perfect, just as long as it is consistent with the order of the numbers. In the previous case, again, I used parentheses because we had the greater than only. In this second case, I'm going to use brackets because I have the greater than or equal. Okay, so that is one set, that's the other set. So you're writing this using interval notation. This is going to go from negative infinity to negative 2 bracket union 1/2 to positive infinity. And that's final answer for this inequality. Alright, so this is the end of this section. I'll see you in the next video.